This is the third video in a three-part series based on section 6.3 in the OpenStax Calculus series, Volume 2, Taylor and Maclaurin series. In this third video, we're going to focus on Taylor's theorem with the remainder. Now, you may recall that the nth Taylor polynomial for a function which is centered at the value x equal a is in fact the nth partial sum of the Taylor series for f at the same center value x equal a. In that case, we can define the remainder based on the number of terms in the Taylor polynomial n to be r sub n is the difference between the function itself and the Taylor polynomial we're using to approximate it. That is, the remainder is the difference between the true value of the series f and the polynomial approximation. In general, the two following statements are true. The closer the x value that we use is to the center value x equal a, the smaller the remainder will be. Let me give you an example. Suppose we set the center value to be x equal 1. If I then want to compare the error that I get, or the remainder, when I use either an x value of 1.1 or 1.3, the x value that is closer to the center of x equal to 1 will have a much smaller error or remainder than the x value that is further away from the center, that 1.3. On the other hand, let's suppose that we know we need to use x equal to 1.1, so that value is fixed. If the x value is not going to change, we can still reduce the size of the error or the size of the remainder by using a higher order of Taylor polynomial for the approximation. The more derivatives we match, the more closely and the wider the interval is over which the polynomial is a good approximation for the function. So the more terms and the more derivatives we take, as n goes to infinity, the remainder, which is the error, will start to approach 0. Now, since the remainder is defined to be the difference between the actual function and the Taylor polynomial, we know that the sequence of Taylor polynomials will only actually converge to and be equal to the function f generating it if and only if the remainder goes to 0. In other words, if this equation can be written as the limit as n goes to infinity, r sub n goes to 0, so that f of x minus p sub n of x equals 0, which would imply that f of x must equal p sub n of x. Now, in order for this to happen, we need to make a couple of proofs. The proofs are really a bit beyond the scope of this course. You could follow them, but they take quite a bit of time and effort that I don't think is worth it for what we're trying to do. However, I do want to give you an overview of how this would be done. You would have to assume that the function does have continuous derivatives up to 1 past the Taylor polynomial that you're going to take. So let's say that you choose to use the 5th Taylor polynomial. Then the function needs to have a continuous derivative up to the 6th, 1 past the 5th, the one you intend to use, on some open interval I about the center x equal to a. The mean value theorem, the same one from Calculus 1, will guarantee that there has to be some x value c in that open interval such that the remainder is equal to the n plus first derivative at c divided by n plus 1 factorial times x minus a to the n plus 1. In other words, somewhere in that interval is a c value, and the value there, when you plug this into the power series formula, gives you that remainder r sub n. Now, quite honestly, finding the actual c could be difficult. Remember that the mean value theorem is an existence theorem. It tells you c exists, but it does not tell you how to find that point. So it could be quite difficult to find the true value of c. So instead, what we tend to do is look for some upper bound on that derivative over that interval. So for example, let's suppose that our derivative involves sine or cosine over some interval. I know for a fact that the value of sine and cosine and all their derivatives to infinity can never be greater than 1. That means that 1 would be an upper bound on all the derivatives for sine or cosine on any interval. That's what we mean by finding an upper bound. An upper bound is just a constant number that you know for sure that that derivative for that function over that interval cannot be larger than. Once you have this value, this constant m, you can replace the n plus first derivative at the unknown c with the m that you found as the upper bound. Nothing else in the expression will change other than the n plus 1 derivative at c is replaced with m. Now, if you can find that, you will be able to prove that the remainder is going to 0. This statement right here is simply the statement all together in one place of all the information we've just conveyed. This theorem will allow us to bind the error, and by that I mean it will give us an estimate for how large the error could be when we're using a Taylor polynomial to approximate a function value. For example, when we're looking at this equation that we had a moment ago, if I know what the value of m is, and I know that I'm using the fifth Taylor polynomial, m is a constant, and this would be 6 factorial since I'm using the fifth Taylor polynomial. I know the center, which is a constant, and again, n would be 5, so n plus 1 is 6. This would give me some expression here for the given value of x that I'm using, which will give me a number that the remainder has to be less than or equal to. This gives me an upper bound and a lower bound for the remainder. In other words, how far off of the true value I really am. Now we want to take a look at an actual example and see how to apply this theorem to a real function. I'm going to choose a function for which we can easily find an upper bound, such as sine. In this exercise, we want to use the fifth Maclaurin polynomial, Maclaurin implying that the center is x equals 0, for sine of x to approximate the sine of pi divided by 24, and we want to put a bound on the error. After we do that, we'll find for what values of x the fifth Maclaurin polynomial approximates sine to within a certain amount of error. First, we want to use the fifth Maclaurin polynomial for sine to approximate this and find the bound on the error. To do that, recall the formula. The remainder, which in our case will be r sub 5, since we're using the fifth Maclaurin polynomial, what we're going to have is r sub 5 in absolute value is going to be less than or equal to some boundary that we'll find, and the boundary must be on the n plus first derivative at some unknown c over our interval, divided by n plus 1. Our n, of course, is 5, so this becomes 6 factorial times, and in this case, since our center is 0, since it's a Maclaurin, this will give us x to the 6th power. Now again, our upper bound is going to be on the 6th derivative of the function at some unknown c value. Now c has to be within the interval of convergence. We know from the work we did in videos 1 and 2 that the Maclaurin polynomial for sine and the Maclaurin series for sine actually converges for all x values when the center is at 0. Thus, we know that we can certainly use any x value and it will be within the interval of convergence. In order to use the fifth Maclaurin polynomial, we first need to find up to the sixth derivative. Go ahead and stop the video, pause it here, and start plugging in the values of the derivatives of sine. You will remember from the last two videos that when we find the sines or the derivatives of sine, that they repeat in a pattern every 4. We need to find the first 6 derivatives and recall that the 0th derivative is actually not the derivative at all. It's the original function. In this case, we don't need the right-hand column since we are not actually looking for the Maclaurin polynomial. What we're trying to find is a bound on the remainder. The bound on the remainder is limited by the 6th derivative at some value over the interval. The 6th derivative is negative sine. The largest value that negative sine can be on any of the real numbers is positive 1. That makes 1 an upper bound on the remainder for the numerator. This tells us that R5 has to be less than or equal to 1 divided by 6 factorial times the absolute value of x to the 6th. The next step is to use the actual x value that was given to us so that we can find the actual error on using the fifth Maclaurin polynomial to approximate the sine of pi over 24. That means that pi over 24 is the x value. So down here we have x is equal to pi divided by 24. That means that we will take the pi divided by 24 and replace it in here in place of x. You may want to pause the video and grab your calculator to crunch out these numbers. After plugging pi over 24 in place of x, raising it to the 6th power, and dividing by 6 factorial, which is 720, you end up with this number here. This is a string of 8 zeros in front of the 6, making it 6 times 10 to the negative 9th power. In other words, this is a highly, highly accurate value for the sine of pi divided by 24. Let's take a look at the next part of this problem. The next part said, for what values of x would the fifth Maclaurin polynomial approximate sine to within 0.0001? In other words, to within 1/10,000th. Let's take a look and see how we would do that. We need the value of the sine of x to be within this number here. That means we need the remainder to be less than or equal to this number here, the 0.0001. To solve the second part of the problem, we need to have the remainder less than 1/10,000th. Since the remainder is less than or equal to this expression here, 1 over 6 factorial times the absolute value of x to the 6th, we will put the strictly less than, the strict inequality, to the right of that. Let's rewrite this below. That means that the remainder must be less than 1 over 6 factorial times the absolute value of x to the 6th, which we would like to be less than 1/10,000th. In order to make this true, I now need to find what value of x leads to that. So I'm going to solve the inequality for x. By solving for the inequality, that means first I need to multiply both sides by the 6 factorial. Multiplying both sides by 6 factorial removes it from the left and places it on the right. Remember that 6 factorial is equal to 720. After this step, we should be left with 1 over, or the absolute value rather, of x raised to the 6th power less than 720 times 1/10,000th. That reduces to 9 divided by 125. In order to get a bound on x, we need to take the sixth root of both sides. We'll leave the x inside the absolute values and take the sixth root of both sides. Since the right side is positive, this should not be a problem. Of course, the sixth root means it is the 1/6 power. You could simplify it a little bit by writing it perhaps as the square root of the cube root or the cube root of the square root, but I think it's fine to leave it like this. Basically, we're now left with a bound on this of the absolute value being less than whatever the sixth root of 9 divided by 125 is. If you use your calculator, you can get an estimate for that by raising it to the 1 divided by 6 power. That is equivalent to the sixth root. This is approximately 0.64499, and of course it continues from there. That means that as long as the value of x is within 6.4 of 0, then we will have that degree of accuracy. Continuing on, the primary reason that we concern ourselves with the remainder is that the only way to determine and prove that a Taylor series for a function f that was generated by the function f, that it converges to the function f, is to prove that the remainder is going to 0. Being able to have an upper bound on the remainder and an expression for it lets us prove whether or not the remainder is going to go to 0. This is the only way that we can be sure that the function which produces the Taylor series is the actual function that the Taylor series converges to. This is given in this theorem right here. That is the only condition under which a Taylor series is guaranteed to converge to the same function which produced it, when the remainder goes to 0 as n goes to infinity. That theorem can be used to show that several of the Taylor series for known transcendental functions like e to the x, sine x, cosine x, natural log, sinh, cosh, all centered at 0, actually do converge to those functions over their intervals of convergence. For e to the x, sine x, cosine x, and a few others, the interval of convergence is actually all reals, which means that we can approximate any value for those transcendental functions with their Taylor series. For others of the Taylor series, there is a more restricted interval of convergence, which means that we can only approximate close to the known center. Again, the Taylor series is just another way of expressing these transcendental functions with known functions that are in fact infinite polynomials. This is the end of this video covering the remainder with Taylor's theorem.